Hello everyone. Today we will discuss how the experimental data can be analyzed. The experimental data obtained from modified shear tests we discuss, and we also discuss how to analyze this data. Today let us discuss what type of a data we obtain from suction controlled shear tests, and also how to analyze this data to interpret the effective stress concept for unsaturated soils we will look into. So, as I explained in the previous lectures, the unsaturated strength parameters can be analyzed by considering two independent stress state variables such as net normal stress and matrix suction. And Bishop is the person who introduced these two independent stress state parameters and lumped into one single equation for defining the effective stress equation. So, using the modified Mohr-Coulomb concept, by introducing this effective stress principle into the equation, one can obtain the effective stress parameter Xi can be estimated, and Xi is a function of either volumetric water content or matrix suction. So, this functional form can be obtained from the experimental data. So, let us understand what kind of experimental data we obtain from suction controlled shear tests such as suction controlled direct shear and suction controlled triaxial tests. And from the data, how to interpret this effective stress parameter we will understand. It is seen that many researchers when they have conducted tests on the suction controlled shear tests, especially suction controlled direct shear test setup, they have observed that the strength of the soil varied in this particular manner. So, when they plotted, so generally in our direct shear tests, we obtain shear stress versus shear strain written in terms of written as gamma, and the stress versus strain relationships for NC soils looks somewhat like this, and for the OC soils it appears somewhat like this, and this is called strain hardening behavior. And this is strain softening behavior, because after this the shear stress decreases. So, it is called strain softening behavior. So, now what kind of results you get? This is a normal direct shear. For saturated soils. And this is for unsaturated soils. So, here you can plot either tau. Here the test is for one particular sigma normal stress. So, here when you plot tau versus gamma, or often this is plotted as stress ratio also. The stress ratio is defined as tau by the normal stress. Here this is the net normal stress, sigma minus UA, because this test is conducted under one particular net normal stress. So, when you control that particular one net normal stress, you get tau versus gamma, that is shear stress versus shear strain. You can also keep changing these values so that you will get a stress ratio versus this one. It is observed that for nearly saturated soils, this is a behavior for NC soils. So, this is for suction UA minus UW is equals to 0. So, this is for saturated soils. So, as you increase the suction, it is observed that it increases in this particular manner. So, this is under another particular suction, UA minus UW is equals to 10 kilopascal. And similarly, when you increase, $50 kilopascal. Interestingly, if you increase the suction value beyond this, it is observed that it behaves in this particular manner. So, let me redraw this with a different color, with different marker color. So, this is the behavior at U minus UW is equals to say 200 kilopascal. And if this is increased further, this is how it changes, and the peak stress, the ultimate stress increases. So, this is the interesting trend you get when the suction controlled shear tests are conducted on unsaturated soils. When the stress ratio kept on increasing, so this could vary in the range of say 0.5 this one, and this can go up to say 2.5 or so stress ratio value, and this can be around say 10% strain. So, interesting trend is that as the suction increases, the shear stress, ultimate shear stress increases, and this exactly behaves like strain hardening behavior. But beyond certain suction values, say more than 50 kilopascal, it exhibited strain softening behavior. It has a peak, which has a peak behavior, peak stress, and after that it reaches to the ultimate. So, this ultimate stress now again keeps increasing with increase in the matrix suction. This is a trend, this is shown by researchers NG and Zhou in 2005 using modified direct shear tests. And further, if you generally these tests are conducted between tau and gamma, that is shear stress and shear strain, under different normal stresses. So, this is at one particular normal stress, and when you conduct with different normal stress, so this is with sigma 2, where sigma 2, this is not principal stress by the way, this is one particular stress, one particular normal stress, and this value is more than sigma 1. So, then as the normal stress increases, the ultimate shear stress increases. So, in this particular case, under the given normal stress, as the matrix suction increases, the shear stress increases, ultimate shear stress increases. Then generally what we do is we in direct shear test for saturated soils, we plot tau versus sigma. So, under different normal stresses, when you conduct the test, you get different ultimate shear stress values, Then when you plot, so you get a trend like this. So this is angle of internal friction phi. If you have an intercept, then you get a cohesion term, but if it is a pure sand, then you will not have any cohesion intercept and you will have only angle of internal friction value. So what kind of a trend we get in this particular case? So here when you plot tau on y axis and you plot net normal stress, that is sigma minus UA on x axis, then for s equal to 0 you get the same trend. So the angle is phi dash. So this is for s equals to 0 kilopascal. As s increases, you see that the critical shear plane, critical straight line also increases. So this is s equal to say 200 kilopascal, and this is for 400, and this is for 850 kilopascal. This SC is nothing but UA minus UW. Sorry, this is matrix section UA minus UW. So this is the trend you get, and the angle nearly remains same. Angle doesn't significantly change. The angle of internal friction value appear to be nearly constant. It doesn't significantly change for different matrix section values, the relationship between tau versus sigma minus UA. So the relationship between shear stress versus net normal stress for different matrix section values, the angle of internal friction value is nearly same. So this is another observation, and often we plot the dilatancy effect. So in our shear stress test, direct shear tests, we have two halves. So this is soil and this is soil again, and you have say porous plate, etc., the top and bottom, and this is connected to a rigid base. Then when you apply load, so this will, there will be a reaction, and this starts moving, and you connect to a dial gauge, and you can note down what is the strain. There is a shear stress that is applied, and shear strain can be determined from this gauge. And also apart from this, there is a one normal stress applied, there is sigma applied, and there is one another dial gauge is kept for recording the strain in vertical direction. So here you get shear strain, and here you get vertical strains. So when you have this kind of a setup, often we measure the dilatancy effect by plotting with shear strain what is the normal strain we get or the vertical displacement you get, that can be observed, and positive is compression and negative is dilation or swell or increase in the volume. So when the volume decreases, that is positive, and when volume increases, that is dilatancy negative. And we often observe that the NC soils behaves in this manner, and OC soils are densely compacted soils exhibit this kind of a behavior. So this is for NC or normally consolidated clay or the loosely compacted sand, and this is densely compacted sand. So these soils exhibit dilation behavior. We have also seen this is because when the particles are in loosest possible state, they may assume this particular configuration, and when you shear, so during shearing operation they eventually roll down to denser packing. So, because of which the volume decreases. So, because of this denser packing, they exhibit strain hardening behavior, and as well as there is a volume decrease that takes place during the shearing. This is with loosely compacted sands. In case of densely compacted sands, initially soil itself is in a denser packing. So, this may be the configuration, and then when you shear the soil, soil particles have to roll up all the way up on these particles. So, this is one particle and this is another particle. So, this particle has to roll up onto the other particle, and because of which the stress increases and it reaches a peak value, and after that the stress drops and strain softening is exhibited because of this particular behavior. And because of this, so the volume of the sample increases initially, initially small settlement that takes place, after that the dilation or increase in the volume that takes place within the soil mass. So, this is observed in saturated soils. Now, if a similar test is conducted in unsaturated soils in suction control tests, then the behavior is shown here. So, the dilatancy is plotted on y axis, and on x axis either normal strain or shear strain gamma or horizontal displacement is plotted. Is plotted on x axis. So, the dilatancy is represented. So, here there is an interesting behavior. For S equals to 0, the suction is 0, u minus uw is equals to 0, it exhibited this behavior, and when suction is slightly increased, this is u minus uw is equals to 0 kilopascal. When the suction is slightly increased, this is the trend that exhibited. This is 10 kilopascal. And interestingly, if you keep on increasing, the dilation increases, so this is the behavior it showed. So, this is maybe at suction value u minus uw is equals to say 400 kilopascal. So, as I mentioned in the previous slide also, that as the suction increases, the soil exhibits strain softening behavior. So, which is similar to, because of that the volume of the sample increases as the shear strain increases. So, as the horizontal displacement increases, the vertical displacement observed on the thing is a dilatance. A dilation is observed in the soils. So, here also, even though sample whatever the condition initially it is, initially when the soil is in a looser state or something, it exhibited similar behavior, but when it has some suction, that some water is present within the soil, something like this, and here when we are shearing, so the particles have to overcome the tensile stresses or tension within the pores, and it has to overcome that, because of which initially it shows a increase in the shear stresses. So, it reaches a peak value, and once this surface tension bonds are broken, then it exhibits a strain softening behavior. Therefore, overcome the surface tension forces in the soil pores. So, it exhibits a dilation behavior similar to a densely packed soils. So, this is a very interesting behavior that we understand from such tests. So, now the question is how to analyze such data to interpret the results in the field. So, the laboratory tests help us in establishing constitutive relationships such as stress versus strain behavior, and once this behavior is very well known, then we can utilize these relationships directly to understand how the failures takes place within the soil in the field directly. So, here we need to establish the unknown parameters. Apart from cohesion and angle of internal friction, these two are material constants, and another parameter that is available, that is known as effective stress parameter. If these parameters are determined in the laboratory for a given soil under different stress state conditions, then the behavior of the soil in the field can be predicted very well. So, earlier I have shown that the Bishop has given effective stress principle, modified effective stress principle for soils, unsaturated soils, which can be written as the effective stress principle given by Bishop. So, this is modified for unsaturated soils given by Bishop in 1959, which is sigma dash is equal to sigma minus UA plus xi UA minus UW. And when you substitute in the Mohr-Coulomb equation or simply the Coulomb principle, the modified theory is tau F at failure is equal to tau equals to C dash plus sigma minus UA plus xi U minus UW into tan phi. Here the interesting thing is that the determination of xi is very complex, but at failure the xif can be determined for known value of stress state. So, at failure, if we know these stress state variables, we can determine the C dash, phi dash and xif. So, therefore, if that is the possible, then xif can be written as tau f minus C dash minus sigma minus UA phi tan phi dash divided by UA minus UW F tan phi dash. So, by knowing the stress state at failure, so the xif can be obtained, and for different values of matrix action can be obtained, because xif depends on either volumetric water current or matrix action. So, xif function in terms of matrix action or theta can be determined from experimental measurements. So, let us see how the experiments are conducted. So, from this particular data, it is evident that when we control the sigma minus UA independently and UA minus UW, when we control sigma minus UA and UA minus UW independently, and when the soil fails at that particular state if these two parameters are known, these two stress state variables are known. So, then by conducting series of tests by varying these stress state variables, we can obtain Xi(f) value. So, let us see how we do it. So, the modified direct shear or suction controlled sheared box test, which is similar to the normal direct shear operators, where you have two halves, where the soil is available and you have a porous stone at the top and bottom. Here soil is available, and here also soil will be available. So, this is a shear plane along which the shearing takes place when load is applied, and this is a coarse porous stone, and this is higher entry disc. And here this whole thing is kept in a airtight chamber, and shear stress are applied, and this one box is confined. So, therefore, the other box can be sheared, and similarly you have dial gauges kept on bottom and top, and there is a provision to apply sigma minus UA net normal stress, and here the air can be controlled inside. So, air pressure can be controlled, and this is connected to a water chamber. So, UW can be controlled through this, and UA can be controlled through this. So, UW can be kept at atmospheric pressure, UA can be controlled to any values. So, that UA minus UW inside the soil can be controlled, and under this suction controlled environment, the shear tests are conducted by varying the normal stress or the net normal stress and UA minus UW within the soil mass. So, at failure, when the soil fails, this UA minus UW at failure is known, and the sigma minus U at failure is also known. By knowing these two things, we can obtain the Xi(f) parameter. Let us see how we estimate. Let us solve a simple example. So, here the data of some synthetic data is generated for understanding how we estimate the Xi(f) parameter. These are at failure, and this is also in kilopascal. So, first set of tests, this is a test number. So, first test is conducted by maintaining a suction value of 0. So, this is a data of sandy soil on suction controlled direct shear. So, when UA minus UW is controlled to 0, that means fully saturated soil. This is typically a normal direct shear test, but here you have a drainage control. So, therefore, so the pore water pressure can be better controlled. So, the sigma minus UA is kept 200 kilopascal. So, then when the sigma minus UA is kept 200 kilopascal, then the tau f, the shear stress at failure, is observed to be 150 kilopascal. So, this is the first test, and when you conduct second test by maintaining a suction value of 20 kilopascal and sigma minus UA is maintained to be 120 kilopascal and tau f is observed to be 105. So, the first test is saturated test, because in our Bishop's expression when UA minus UW is equals to 0, it boils down to Terzaghis expression. Then anyways, this is a sandy soil, so the C dash is not present. So, only phi dash is present, and phi dash can be now determined using the first test, and subsequent tests would help in understanding how Xi f changes with change in the suction value. Knowing the phi dash, which is nearly constant, that is observation I had shown in the beginning, that the phi dash nearly is constant. So, the increase in tau dash with increase in UA minus UW, and the changes in tau versus sigma minus UA for different suction values is similar, and in fact, the critical state lines are parallel to each other. So, therefore, phi dash could be nearly same. So, therefore, we are assuming that phi dash remains same, and then therefore, when suction is increased, how Xi f changes can be obtained. So, therefore, the tests are also conducted in the same manner. One test is conducted at saturated and other tests are conducted at unsaturated conditions. And 50 kilopascal, and similarly 200, 500 and 800. Nearly 6 tests are conducted. 6 tests are conducted under 50 kilopascal. This is kept constant after first test. So, because suction value is varied, the tau f started increasing 172, 240 and slightly decreased here onwards 210, 205. So, now this is the measured data. From suction control tests, and this need to be estimated, this one. The Xi f value for the first test, because it is a saturated soil, the sigma dash equals to the Bishop's effective stress principle, sigma minus UA plus Xi f UA minus UW. In this, if Xi f becomes 0, this is completely dry test, dry soil, and Xi f equals to 1, that means these two get cancelled and this is sigma minus UW. This is the effective stress principle for completely saturated soils. So, therefore, Xi f needs to be 1, and this particular condition UA minus UW equals to 0 should not be substituted in the previous equation. The previous equation is Xi f is equals to tau f minus C dash minus sigma minus UA f tan phi dash by U minus UW at failure tan phi dash. So, here if you substitute UA minus UW is equals to 0, then Xi f becomes infinity, it does not have any meaning. So, here we know that this effective stress principle itself is that sigma minus UW. So, if you substitute directly, and anyways Xi f should be 1. So, we do not need to substitute here, there is no U minus UW, that is it. So, Xi f maximum value that can take is 1. So, maximum value is 1. Xi f infinity means in fact the maximum value is 1, that also can be said, but the Xi f value should not be obtained from this equation by substituting u minus uw equals to 0. Otherwise, if you interpret that the maximum value of xi f is 1, therefore, xi f equals to infinity means xi f is equals to 1. So, other values can be obtained by first by obtaining the phi dash value. This is a material constant. So, if the phi dash is obtained, then other values of xi f with u minus uw can be obtained. So, from the first equation itself we can estimate that tau f is equals to sigma minus uw So, the effective stress, the applied stress is nothing but effective stress at that particular point. So, therefore, phi dash is equals to tau f by sigma minus uw. The applied stress sigma minus ua is nothing but sigma minus uw now, because the total stress becomes effective stress when the pore water pressure completely dissipates. So, therefore, phi dash is equals to tan inverse of 150 by 200. So, this is equals to 36.9 degrees. So, if this quantity is known, this is the material constant which this value is known, then other values can be obtained by varying the u minus uw, that is it. So, for one particular data, that is second test, this is tau f is 105 minus c dash is not there. So, this is sand, and sigma minus ua is 120 tan 36.9 degrees divided by u minus uw is 2 at failure tan 36.9 degrees. So, this is equals to 0.9923. So, this xi f value is 0.9923 when the u minus uw is equals to 20, and this value is 0.824 for u minus uw is equal to 50, and at 200 this value is 0.593, and at 500 this value is 0.169, at 800 this value is 0.098. So, this is how the xi f can be obtained from the modified direct shear test data. Let us see how these values would vary. So, this is the variation of SWCC. This is normalized volumetric water content versus suction in kilopascal. Generally, the trend is like this. So, if it is plotted on a normal scale, so then the variation of xi f is the normalized volumetric water content, say varies from 0 to 1, and xi f varies from 0 to 1. So, the variation is linear, it could be linear like this. So, there is a problem with the pen. So, this does not appear to be linear, but this is linear, right. So, there is this is how the xi f varies with volumetric water content. If it is with suction, as the suction increases, xi f becomes smaller and smaller and it goes to 0. This is 0 to, so say 800 kilopascal or something, and this is 0 to 1. When the suction is 0, this value is equals to 1, and when suction is very high, this value goes to 0. And the experimental observation shows that this need not be linear also. On some cases it may be non-linear, and it could be varying like this, or it could be varying like this, etc. So, there are several empirical equations proposed to estimate Xi(f) value. So, one such a empirical equation is, which are given in Liu and Lycos. These empirical equations are derived by several people like Khalili, etc. One of such empirical relationship is Xi(f) is equals to psi m by psi e power minus 0.55 when u minus uw are Xi m, there is a matrix action, while u is more than Xi e, and this is equals to 1 when Xi m is less than or equals to Xi e. So, what is Xi e? Xi e is a suction corresponds to air entry for drawing data or air expulsion pressure. For pressure for wetting data. So, what does it mean? When if you have a soil water characteristic curve data, if you plot on semi-log, x-axis log scale, then you will have a relationship somewhat like this. So, this is for drying data, so this is for wetting. So, this particular point, wherever this deviates from 1, that is the air entry value. This is psi e air entry, and here this particular point is psi e 2. So, this is for drying, this is for wetting. So, because we have seen that there is a hysteresis exists for soil water characteristic curve, the drying data exhibits a different trend compared to the wetting data. This is initial drying and this is main wetting. But if you do a main drying data, then it shows a very good hysteresis data like this. So, this point and this point again merges. This is main drying. So, essentially initially when normalized volumetric water content data is 1, then Xi value is 1, and if the normalized volumetric water content theta value is less than 1, big theta is less than 1, then Xi(f) value takes this particular form. So, corresponding matrix action will be substituted, and this is the bubbling pressure in case of drying soil, and this is air expulsion pressure for the wetting soil. When you substitute, power minus 0.55 should give you Xi(f). This is an empirical relationship based on several observed measurements from the suction control tests. Similarly, you have another relationship that is available, that is very simple, second empirical relationship, that is Xi(f) is equals to theta by theta s power k, or simply xi f is equals to normalized volumetric water content, that is theta minus theta r by theta s minus theta r. Here theta by theta s power k, when the k values change, the non-linearity between volumetric water content and xi f value change. So, for example, I will plot it here. So, this is xi f and this is theta, big theta. For k equal to 1, this exhibits a linear relationship. For other k values, for example, k equals to 2, it exhibits this behavior. For k equals to 3, the non-linearity increases. This is how it varies. So, however, anyways we have a very limited data from the suction control shear test, because there are several limitations associated with these tests. One major limitation is that the maximum suction range would be in the range of 1500 kilopascal. If we are controlling the suction in the shear test by utilizing axis translation technique, or it would be around 1000 to 2000 kilopascal if we are controlling the suction by controlling the suction osmotically. In osmotic control test also, the semi-permeable membrane would start degrading after nearly 10 days. This is the research outcome by some researchers. So, because of these limitations, the equilibration time requires for the soil to establish, for the soil to come to one particular suction value takes time. So, within this equilibration time, if the semi-permeable membrane degrades, then it allows the PEG solution to go into the soil. So, because of such situations, there is a limitation on the available data, especially for fine grained soils. Most of the data that is available is for either sands or silt soils, and that too the measured shear test data in a small range of suction values. At very large range of matrix suction values, only recently this is attempted by controlling the suction within the shear test by vapor equilibrium techniques, and combining all these data and considering the initial compaction states etc., the tests would be more complex and the analysis is very tough. So, these are the some of the major limitations we have with the test data. Apart from that, as the matrix suction value increases within the soil mass, the shear strength increases, but this does not increase linearly, or this cannot be a direct proportionality to suction value. That is because we have seen in our basic soil mechanics that the strength behavior of sands in completely saturated state and completely dry state is same. So, the factor of safety for infinite slope behavior of sands when the soil is completely saturated or when the soil is completely dry, the factor of safety remains same, because the angle of internal flexion is phi dash only. But however, due to the presence of small water film within the soil mass, there is a surface tension that is available, which increases the strength of the soil. So, this increase in the strength, that is with the increase in the matrix suction, the increase in the strength of the soil is not proportional, directly proportional for the entire range of matrix suction values. So, even though as the matrix suction increases, initially the shear strength of the soil increases, but beyond certain suction values, the shear strength should drop and it comes to again back to the same value as it has initially at fully dry state. So, such concepts could be developed if more and more experimental data are available. So, based on the measurements, we can build develop models, we can develop better constitutive models for understanding the behavior of unsaturated soils. Thank you.